So, our next speaker is Xiongfeng from Tsinghua University, and he will tell us about semi-self-testing quantum random number generation. Or different, different types. Quantum random number generation with untrusted devices.
Yeah, I think I should really put the semi-self-testing here. First of all, I would like to thank the organizer to give me this chance to introduce some of our research works. This work is done by many of my collaborators. So here I will just mainly put two of my students, Xiaoyang and Hongyi Zhou, who basically helped me prepare these slides. Alright, so first I will give you a very brief introduction about the quantum random number generation. It's good that in the previous two talks, some of the concepts in my talk is already introduced. That makes my life easier. And then I'll talk about the two of the semi-self-testing quantum random number generation. One is the source independence, the other one is MDI. And then finally I'll give some of the open questions. Alright, so as introduced by the previous talk, randomness is really important in our daily life, especially in the cryptography and also a lot of computation, Monte Carlo simulation. We know that the crypto systems really requires information theoretical randomness. So we know that if we allow a little bit bias in your random number generators, so no matter how smart you design your crypto system, it will be insecure. So if you check so basically I just quickly Google online, and we can see lots of problems and backdoors introduced by the random number generators. So there are a few types of the random number generators. So one is the software-based super random number generation, so which is deterministic. So we know that if you weight a lot, so for any deterministic algorithm, you cannot increase the randomness. So as long as you have inputs the C randomness, then that's how much randomness you can generate. So and then we also have physical random number generator. So previous, let's say if we look at 20 years ago, we have lots of so-called hardware random number generators, which is based on the touch the. It's too fancy. Yeah. So for this one, so for most of our previous physical random number generators, which is based on chaotic processes, like for example, if you measure the temperature of the CPU, so it's kind of random. Okay, it's kind of random. But the problem is that the randomness is unknown. What's the randomness origin? It's unknown. We don't know. So why it is random from the physics? Actually, in some special cases, we can prove that the generation speed of this kind of random number generators is not so. For example, if some of those random number generators, they claim that the speed is let's say 100 gig bps, and then if you really carefully model the whole system, you will see that actually the entropy of that kind of system is less than that. Then we can from there we can quickly see that that kind of random number generators, you must have some bias. So finally, of course, the random number generators are based on the quantum process. So we most of us, I would say, we agree that so this randomness is genuine. Alright, so if we really look at the origin, the randomness origin from the physics, so basically it's come from the breaking of the covariance. Sometimes we also call it breaking the superposition of the true state. So that's the only, actually it turns out that that's the only origin we can, randomness origin we can get from the physics. Of course, that's also a big problem in the beginning of the quantum mechanics. There's a big debate between the Einstein and Bohr, which is essentially on this whether the measurement result can be random or not. So let me just give you a quick example. So from Schrödinger's cat. So if we have a classical box, then if we have a box, there's a cat in the box, whether it's dead, whether it's alive or it's dead. So which is quantum, which is classical. So basically it's just a classical case. And then we also have Schrodinger's case, which is quantum, so which in the superposition. So the difference between these two cases, that's the this case is state in a classical mixture between two states. And this one is a coherence superposition. So the big difference is that whether you have coherence in this state or not. Okay. So actually, recently there's a lot of work in terms of measuring the coherence. We also propose some of the. It turns out that the randomness, intrinsic randomness, is closely related to the measure of the coherence. So, for example, let me give you a quick example. Suppose you have a quantum states rho, and then you also have a given basis, measurement basis m, and then you ask a question: how much of the coherence you have in this density matrix rho? One of the measurements you can have is that suppose if holds the purification of this rho, and then if you ask a question that's if you perform this measurement, how much randomness you can have, conditional on Eve's measurement results. So now Eve's information is already classical. Okay. So given this one, we can characterize the randomness. So here I just use the Xiongfeng entropy here. Later on I will come back to this one. So for simplicity. And then it turns out that this kind of randomness is a good measure. It turns out that it's a good measure for coherence. We can also assume that if does not perform this measurement, so if system is quantum, so suppose we have this quantum conditional entropy, we can also use the mean entropy to replace this Xiongfeng entropy. It turns out that this measurement is also another coherence measure. So this one, actually we call it the so-called coherence formation. The name is borrowed from the entanglement measure. So this one is the relative entropy measure. It turns out that there's a difference between these two numbers, which is quite clear for us. Some of the audience when we're working on this quantum conditional mean entropy or its classical conditional mean entropy. And then interestingly, the difference between these two numbers is the discord between the Alexander system. So which the result is shown in the recently we put on a type just last month in May. So and then so let's come back to the random number generation. So now we know that as long as we can break the coherence, we can get the random numbers. So we know that in the past 15 years or so, since 2000, the first experiment is done in the Zaibinger school. And then since then, there's lots of developments on the random number generations. Most of them are very fast, stable, and very kind of quite cheap. So we have discrete variable random number generators, like the first one, and also we have continuous variable based random number generators, like the one done here by Professor Pan's group, and the speed it can go up to 68 BPS. So it's really fast, and also all the components in the random number generators, you can just purchase all the components commercially. So you don't have to build up single phone detectors for this kind of products. So we also have a review paper on the subject, so which will be appeared in the MP3 quantum information. Okay, what's the problem? Okay, before we talk about the problem with these very fast, cheap random number generators. So let's take a look at the details of this kind of random number generator structure. So we know that a typical random number generator can be decomposed into two modules, so which is very similar to the TYQI system. One is the randomness source, the other one is the readout system. So randomness source, so as we just introduced, it must be staying in the superposition of two states. And it contains coherence corresponding to the measurement basis. And then the measurements will break the coherence so that you can get the randomness. Side remark. So in many random number generators, a short seed is required to assist state preparation or measurement, like the one that just we introduced in the previous. Okay, I should Okay, so and it turns out that the device characterization is difficult. So we try to model this kind of those very, very fast continuous variable quantum random number generators, try to make sure that the randomness is genuine. It turns out it's really, really hard. And also, bias can be introduced by unknown device imperfections. Especially when you bought some device, if you buy some device from some unknown resource or some companies, they might put some backdoors in your random number generator. That would be a big issue in the crypto systems. Okay, let me give you one quick example. So suppose when you buy some device, so you ask the manufacturer to give you prepare the states like plus states H plus B, and then you perform measurement H and B. So in this case, we know that the numbers, the measurement outcomes will be random. However, the manufacturer might input some just H and V, but it's just puts the H and V in a random order. And then if you perform the measurements, you will see that okay, it looks like it's still random. But it's not generally random because the manufacturer can have a copy for this one. So in this case, even manufacturers themselves, they cannot have a copy for this one. So this is a big problem. So how can you make sure that your device is honest? Okay, so we just introduced the device independent random number generation. Okay, so the schemes are proven to be secure by these two groups. We have children in the audience. And then, so I will just skip this part. So we can make it device independent. Okay, what's the problem? The problem is that the generation rate is too slow. So if you look at the RIN's demonstrations for this kind of protocols, the generation is extremely slow. It's typically it's like a few bits, even like a few bits per hour or per day. So that's not even close to the 6 to 8 BPS. And also that kind of speed is required in the QPD system. But if we talk about the 1 gigahertz QPD system, what you really require is the 10 gig BPS roughly, 10 gig BPS random number generation. Okay, so what we have here is that we try to say that okay, we can make it somewhere, okay, it's really secure, device dependent, and also we have a very fast, very cheap, practical ones. Can we have somewhere in between, balance the security and the performance? Okay. So one is the source independence, one is MDM. Okay, I need to point out that one of the RIN's works that which are online is that so basically again it's based on the continuous variable source independence random number generator. It can go up to BPS. So that means that it's already, even for this kind of source independence even you don't trust any source of devices, you can still have a very practical performance. Right, so the optical implementation. So again, optical quantum signals from the source supposed to go through some modulator to actively choose between X and Z bases. So basically, to actively choose between two bases, you need some random seed. You choose the X basis to test the source, to use the Z basis to generate the randomness. Okay, and also in the system, normally we assume we have 2 detectors, so there are 4 possibilities in practice. One is no click, so like losses or vacuums. 2 single clicks, 0 or 1, good ones, and also double clicks. So later on we need to deal with all these practical issues. So here we assume that the source device is untrusted. Okay, it's arbitrary. But we do trust the measurement device. So that's what we call the semi-self-testing. Okay, so then if we trust the measurement device, we have to put some requirements on the measurement device. So we say that we just use one sentence satisfies the assumptions in the squash model. So later on I will introduce a little bit more details about the squash model, which is already widely used in the QPD security analysis. So the idea is that, okay, so suppose the point is that when you do not trust the source, the problem is that the state might not be a qubit. So we have to have some way to squash down arbitrary big source states, and then you need to squash down to a qubit and a vacuum. Also, we allow vacuum coming out here. And then you perform the measurement of the X measurements, you just make sure that it is a path state. And then you use databases to generate the analysis. So that's the main idea of the work. Okay? So the source, again, the source is prepared by a untrusted party. Okay? And then it's in arbitrary and unknown dimensional space. For the measurement side, we swashing down to a n qubits and vacuums. Okay, so of course vacuums come from losses and detection efficiencies. We need to do some random sampling. So we pick up Alice randomly pick up nx out of n. So normally nx is much smaller than this n. Okay, so when n is big, and then you measure in the x basis to make sure. So the results will be plus or minus. So hopefully, ideal case will be all the results will be positive, and Alice will be happy. And then for the generation, so you measure in the basis. Okay, the Swatch model. So this is the Swatch model paper for the QPD, which can be directly applied to our case. So how we need to evaluate? We need to evaluate the bit error rate in the x basis. So if you get a minus sign, then you call it an error. And then if it's double click, we call it half an error. So this is required by the Swatch model. And then we can calculate what's the bit error rate in the x basis. And then so again we apply the short price scales QTD scale proof technique here. So this the bit error rate in the x basis will be similar if you look at the j basis will be just the base error rate. Okay. Of course, there's some deviation because you use random sampling. You allow some statistical deviation. Okay. So eventually, we use this error correction technique. So what you can do is that if you, in principle, you can correct all the phase errors, then you can get all the plus states. Then if you measure the j base, you should get all the random bits. So that's the technique. So if we look at this term, so this is 1 minus h of the phase error, which is appeared in the short scale proof. So we have a little bit extra terms for the hashing, let's say from total basic hashing. So this is again caused by the finite key finite data size effect. So because even you know the error rate, still you have a small chance if you use hashing, still you have a very small probability that the error correction is a failure. Okay, here I have a note here. So here I need to emphasize that this H is Shannon entropy. So normally in the randomness quantification, we should use mean entropy instead of Shannon entropy. Actually, you can have a very very easy convex sample show that the Shannon entropy is not, in general, Shannon entropy is not good quantification for randomness. Actually, last year in the Michigan, so previous TYQI congressman, Professor Bossard made a comment say that, okay, in general, Shannon entropy is not a good quantification. But if you say that if your Shannon entropy is 1, then it turns out it becomes a good measure for the randomness. So that's the main idea behind this one. So if we correct all the errors, so suppose let's say suppose we don't have a failure probability for error correction, then your entropy becomes 1. Alright, so and then analysis. So I will skip most of this part. So I also need to point out that there are also small practical issues we need to deal with. So this finite key analysis, I will just skip all those practical issues. And then so we submit the paper in 2014, and then it comes the review comes back quite good. And then in the paper we say that it's really very practical. So basically it's extremely easy to implement it. And then the referee suggests say that okay, since it's so easy that you should do it. And then of course I'm a theoretical group, so it's really so almost get accepted in the end of 2014, and then we spent more than half a year to do some experimental demonstration for that, which actually we borrow the QPD kind of a tutorial QPD system from the Quantum C-Tech, so which is also sponsored for this workshop. So and then we do a quick demonstration, and then which cost us like more than half a year, and then published earlier this year. So, and then we also have the experimental results, statistical tests. And then we say that some people may actually say that, okay, now you assume that the source is insecure. You trust your measurement device. What if you do it the other way around? Measurement device integrity. So the idea is very similar. So you can use source to characterize your measurement device. And then if you don't trust the measurement device, if you trust the source, as long as you can characterize the measurement device, you can still get the security. It's more or less like a dual problem with the source independent random number generator. So the only tricky part here is that in the source independent that one we already have a squash model in the QBD, but this one we don't have that. So that's the tricky part. So that's we spent lots of time kind of developed a very similar squash model that kind of argument in this NDI case. And then in the paper, so now we are a little bit more smart. So we say it's practical. It's not that practical. So the external manager we are collaborating with the Professor Xiongfeng and Jun Zhang at USDC working on this one. So the technical paper is published last year. Okay, so I will skip the this procedure since I'm running out of time. So again, the idea is very simple. It's just use the testing mode to test your measurement device, pretty much like a measurement tomography, and then you just use the generation mode to generate the random numbers. Alright, so I will skip the detail. So, and then since we are on the randomness, I just do a little bit advertisements on one of our recent work. It's on the binary factor. So suppose we have a classical coin, okay? So the probability to get hit with probability p. And then, of course, I don't tell you the value of p. If I ask you to generate another coin, which has a probability have had, let's say 2p, let's say. In general, it's a function of p. It turns out that the set of the constructible function of the p is very limited in the classical coin. And then the quantum coin can do actually strictly larger sets. For example, f equals to 2p. It cannot be constructed with the classical coins, but it can be constructed with the quantum coins. And then this is we call the quantum binary factor, and then we implement this result in a superconducting qubit system, and then it's accepted by the so which is again is very related to the quantumness. Finally, we want to say that's the future projects. So we want to hopefully, if in the end, we want to replace the tomography with witness, which can simplify the setup. And also, we want to extend the analysis of the NDI to the most general attacks. So in the end, what we really want is to design a quantum random number generator, which is we can tolerate large losses and generate fast random numbers simultaneously. So basically, with given the minimum assumption of practical setups, so make it more practical. So that's all. Thank you.
Okay, so I see people closer to me first.
Your untrusted source, quantum random number generator, do you assume the source is untrusted but honest? Or do you assume the source is untrusted and evil?
Oh, can be evil. It can be evil.
So you can go and control your detectors or do some hacking attacks. Is the scheme tolerant to that if the source is literally supplied by your enemy who is versed in technology?
Okay, so in this case, when we say source independent, that means that the source can be produced by your enemy directly. Of course, so the source only has control on the source side, not the measurement side. Okay, we still trust the measurement device. And maybe for the NDI, the other way around.
Next question.
So you said it's about coherence in your randomness. So this reminds me to our 2010 paper where we proposed to use the vacuum measurement. And what we highlighted, of course, is that you need few states. So when you say it's about coherences, I guess that's the same as saying that you need few states when you want to have quantum random number generators. And that's basically what you said with your other method then, the test. It reminds me of a paper of Paul Creat's group, really very old paper of Paul Creat's group, where he had a random number generator with the self-referencing and self-tomography. Is that similar to that?
So I'm not too familiar with the paper you mentioned, but the point that so when we talk about the pure state and coherence, actually it's not necessary to be a pure state. So even for a mixed state, you still have some coherence. Of course, if it's a pure state, then your coherence can be maximized. So in general, when you do this tomography or you do this testing, often what you get is the mixed state. But still, we can quantify the randomness out of this mixed state. But the paper you mentioned, I'm not too familiar, so probably we can talk offline.
This question at the back on the left.
So in your random number generation, how can you certify the random number is from quantum process instead of classical process? Or in other words, do you have any test to certify the quantum randomness?
So that's the difference between this fully device independent quantum random number generator and the semi device independent quantum random number generator. So this one we cannot certify directly from the data itself. So what we really can do is that we need to model parts of your system. Let's say, for example, in the source independent case, we need to model your matching device. As long as if you can trust this modeling, or you can trust your matching device, then the randomness is genuine. So similarly in the MNI case. So it is different from the previous talk. So just look at if you assume that no communication between two devices, and then if you look at all the data, then you can generate randomness. That's a slightly different point.
Paulo? Next.
Please, may you comment on what is the effect of finite key in the case of this experimental work you presented? Because it's a relevant point and has been addressed also, for instance, in another application, not the one you referenced from our group, but an earlier one on discrete variable and with untrusted source. And yeah, you see a very clear, say, difference in the finite key case. So what's your point in your recent presentation?
So in our case, it's so for the finite key analysis, that part is it comes out that just from the theoretical point of view. If we deal with if you are dealing with the discrete variable fundamental number generator, it's quite easy because all the techniques you can directly get from the we can directly borrow from the QPD all the analysis. So basically, it follows like random sampling, or we can use if we look at the error correction, what's the probability for the failure probability for the error correction. So that's easy. But if we go to the continuous variable case, it will be a little bit more complicated because so the key point that's as we know from especially for those works by nice works by Random, say that's if the dimension go to infinity, some of the techniques like a definitive film cannot be directly applied. So we have to use kind of other techniques to overcome that part. So that's what we are interested in this case. But I believe that can be done eventually. It shouldn't be too different from the discrete variable for the key.
Question?
So could you comment a bit on this squashing operation? You can trick by this.
Okay, let me go to that page.
How does it work in practice?
So in practice, it's like so you basically it's like again. So this one is a model we call it squashing model. So this one it kind of in this model you have to. So suppose you have a measurement setting. So you have to make sure that your measurement setting is compatible with the squashing model. So for example, in this paper, they propose say that if you use a threshold detector. Again, over there, what they really assume is a single, almost like a single mode threshold detector. Of course, it can be extended to the multimodal case as well. So in this case, if it's single mode is a threshold detector, actually you can mathematically prove that it is equivalent to the squash model I mentioned. It's like object dimension you just project to the qubit and the vacuum first. So the idea is that the fundamental idea is that because your outcome, you only have two outcomes, either 0 or 1. So it's easy. I mean, intuitively, it seems to us it's like if you only have two outcomes, it seems to us it's like that outcome is come from a measurement on the qubit. Of course, these qubits might not be the qubits you prepared initially. It could be because it's affected by other dimensions as well. So that's the key idea about this structure model.
Thanks. Is there any question? Okay, let's thank Xiongfeng. Time for announcement. The